This is going to be a bit of a funny presentation because I'm not going to talk a great deal about the SLS, but I am going to talk about research that started off from the SLS and then went into a slightly different direction, which is a rather nice example of how, to me, of how research actually works in practice and the difficulty sometimes of planning it. And I think it shows another dimension of the value of something like the SLS that enables researchers to get ideas together that then take them off doing different things. We started off with a project, this is about 5 years ago, which was going to look at population ageing and mortality in Scotland using the SLS, but using its link to the vital events register for the mortality data, and using the 5% sample from the 2011 census. As you're probably aware, there was a bit of a delay in getting the census results into the SLS and to making that linkage, and that left us with about a year during which we were kind of sitting around thinking what else we could do, which sent us off in search of other useful data, and also sent us off thinking more theoretically about some of the things that we were trying to do. The first set of ideas we had was around the way in which most discussions of population ageing refer back to or use figures from the old age dependency ratio, which calculates the number of people over the state pension age and divides it by the number of people who are age 16 up to the state pension age. And that's supposed to give you a ratio of the people who are drawing pensions benefits or who are potentially dependent in their old age, and the people who are young enough to work and pay for them. It's difficult to think of a worse way of calculating that ratio. If you look at what's happened to the labour market over the last 50 years, it's been vastly increased by the much stronger participation of women in employment, the decline in the male breadwinner system, the rise of dual earner families. There's also been a dramatic drop in the number of people entering. Hardly anybody enters the labour market at 16 anymore. Most people enter the labour market in their 20s. Similarly, relatively few people retire at the state pension age. Only about a third of people work on to the state pension age. So why use the population age 16 to 65 as your denominator when, thanks to modern technology and the more nimble nature of survey and census work today, we have a very accurate record of the number of people actually working. Indeed, why just base it on the number of people actually working than their productivity, because that's what counts at the end of the day if you're wanting to pay for things like pensions. We thought that the last jump was probably a jump too far for most policymakers and so on. So instead what we did was come up with an alternative to the old age dependency ratio, which calculated the number of people whose life expectancy was 15 years or less, regardless of the age at which they might ultimately die, as a proxy for people who may be in some way or other dependent. It's a rough and ready figure. You could have chosen 10, you could have chosen 5, you could have chosen to calculate it in a different way. But I'll come back to why we wanted to count backwards from death rather than forwards from birth in using that figure for an estimate of the size of a potentially dependent population. And then in to calculate the workforce, we just used data on the actual size of the workforce. And we then looked at, well, what happens when you compare our new measure of the dependency ratio against the old traditional old age dependency ratio. The figure, these are for different European countries. The lines in thick continuous print are our new measure. The dotted lines are the traditional OADR, old age dependency ratio measure, and we're covering the period, God, if my eyesight was better, I could tell you, 1958 up to, I think we stop in about, we stopped just as the crash is starting. It'd be nice to go back and update some of these figures. Anyway, the story of the graph's perfectly clear. The old age dependency ratio is increasing everywhere. Our dependency ratio is decreasing everywhere. Now, why should that be? Well, the answer is, unlike people, populations can get older and younger at the same time. We got interested in thanatology, which sounds like a... Oh, sorry, let's... Before I talk about thanatology, I'll just say, if you're interested in that line of work, we did an article in the BMJ a couple of years ago that described it. We got interested in thanatology, which sounds like a Hollywood cult, but isn't. It's simply the practice of counting age backwards from death rather than forwards from birth. So if somebody lives for 95 years, when they're born, their chronological age is 0, but their thanatological age is 95. When they die, their chronological age is 95, their thanatological age is 0. Now, you might think this is a straightforward arithmetic operation. Huh? It's just a question of counting in two different directions. And for an individual whose date of death is known, that's the case. For populations, it's absolutely not the case. And the reason for that is the decline in mortality, which is driving expanded lifespans, which means that for any period that you care to identify, we talk about the 1960s, the 1990s, or whatever, the average thanatological age corresponding to the average population age will be different. That's just another way of saying, in 1900, somebody who was 65 was very old. Today, somebody who's 65 can expect another 20 years of life. Now, if your measures of what's happening in population aging are based solely on chronological age, you're going to get systematic distortions, because it's not going to take account of the way in which any individual chronological age, the significance of that age will change over time. And our case was that insofar as all kinds of issues to do with population aging, whether it's the pension system, whether it's the prevalence of morbidity, whether it's the demand for healthcare and so on, insofar as all these estimates and predictions are based on chronological age, they're likely to be systematically biased. And let me give you a little sort of illustration of what that. I'm going to skip this slide because it's on a shockwave thing that won't work. This will give you another idea of what I mean by thanatology. On the left-hand side, we've got the traditional population pyramid for the population of Scotland in 1950. I'll come on to the colours later on. Like any population pyramid, it's got those aged 0 at the bottom, and then each single year cohort up to a few lucky people aged in their 90s at the top. The graph on the right-hand side, which we call the population leaf, just because of the shape that they typically take, does the same for thanatological age. The people at the bottom are those who are about to die, who are in their final year of life, and we increment up thanatological ages up to the very top, are those who have got a very high thanatological age, which would be, for example, babies born today who will be lucky enough to live to 100 or 105 or whatever else it might be. Now, obviously, we don't know what's going to happen to individuals, but for populations, we can calculate the probability of the distribution of life expectancies fairly straightforwardly. You can think of a population pyramid as one where we know where everybody enters, but we don't know where they leave. So we don't know at what age the people who are currently aged 1 year are going to die at. Yeah? Similarly, in the thanatological age pyramid, or the population leaf, we know where everybody leaves, but we don't know where they enter. Yeah? And you can flip backwards and forwards from one to the other fairly easily. Now I'm just going to run an animation of what happens in Scotland from 1950 up to about 2010. You see this little blip, that's the war, the post-war babies, and the population boom starts. Look what's happening to average ages. The average age of the population stays around the low 30s. Then as the baby boom wanes, the average age of the population starts to rise because of the effects of declining mortality and so on. But if you kept your eye on the average remaining years of life of the population, which is what we get from the population leaf, you'll have seen it's increased as well. It hovers around 40. It goes from a bit under 40 to, I think, a bit over 40 at the end of the period. The other thing to note is population pyramids there's baby booms and busts, so they're quite erratic in their shapes. Population leaves are remarkably stable. You might have a dramatic change in the number of babies born from one year to the next. There is hardly any change in the number of old people who die from one year to the next. And simply because everybody's born at age 0, but people die at a variety of different ages. The last of the baby boomers in the United States will die sometimes towards the second 2/3 of this century. And so there's a number of things you can draw. Let me just do a quick comparison of. There's 1950. There's 2011. Everybody's familiar with the change in shape of population pyramids to the so-called coffin shape, as declining mortality pushes up average ages. They're not so clear about the way in which the shape of a population leaf is remarkably constant. So some of the things that we kind of conclude from that is ideas of an impending wave of baby boomers hitting health services or care services for the elderly and causing unsustainable strains on public services are simply mistaken. People age at different rates. There won't suddenly be an avalanche of dependent elderly descending upon the NHS. Let me just go back to the PowerPoint. And do one last thing about all this. Some of the work I've shown so far is just sort of probabilistic, using data that we have on the likely life expectancies, the distribution of likely life expectancies within different birth cohorts or age cohorts. However, if we've got longitudinal data on people's entire lifespans, then we can look at things like not just the distribution or prevalence of morbidity, but what the correlates of the onset of different health conditions or morbidities or life transitions are in terms of age from birth, chronological age, and time to death, pharmacological age, on the other hand, and see which of these two explanations is more important. Obviously, they're both going to be important, but what's the sort of balance of probability? Here's two fairly incomprehensible graphics from a study we did of the US Health and Retirement Study. The nice thing about that is it's a population-based sample of older people both in private households and in institutional households, so that we don't have the bias imposed by normal household-based surveys. And it has a very good mortality follow-up. So we took the cohort of people born 1915 to 1919 on the basis that almost everyone from that cohort has now died, and looked at their responses to the survey over the 20 years or so from about 1992 to 2011, which allowed us to capture data on the onset of different health conditions or life transitions and so on. We then produce, these are kind of like sort of kinky Lexis diagrams or reverse Lexis diagrams. On the vertical axis, you've got time to death or pharmacological age. On the horizontal axis, you've got chronological age or how old people are. And the heat maps are just the incidence or prevalence of a particular condition. And the top one is psychological problems for males, basically dementia. The bottom one is back problems for females. And the darker the shade, the heavier the influence. You can see the first one, it's absolutely pharmacological age that drives it. Chronological age is almost irrelevant. In other words, the patterning of the heat is almost horizontal. Yeah? In other words, dementia, Alzheimer's, similar conditions are a function of how long you have to live, not a function of how old you are or how long ago you were born. In contrast to that, back pain is an example of the exact opposite. It's absolutely a function of how old you are. It's got absolutely nothing to do with when you're going to die. Now, we're able to look at about 86 different conditions in terms of these two dimensions, and summarizing, heroically and badly, about 2/3 plus of the explanation comes from thanatology and about 1/3 from chronology. And if that's the case, all currently existing estimates of things like the future prevalence of morbidity, the future demand for social care services, the future demand for health services are systematically biased. They're likely, insofar as the decline in mortality continues and has the same kind of effects that we've seen here, which is for one country and for one birth cohort, so I don't want to generalize too much, but if that cohort is in any way typical, and there's no reason to think it's dramatically atypical, then we have to pay a lot more attention to time to death when calculating the effects of population aging. All of which is to say, my final conclusion is that what I always say when I talk about population aging, how have we ever come to think that population aging is anything but a good thing? Population aging is just about people living longer. The only way in which we've been encouraged to think of it as something negative is by making a completely illicit analogy between the lifespan of an individual person and the age structure of a population. And the two things are completely different. Individuals can't get older and younger at the same time. Populations can. So